All right, and we are back. Connection seems to be a little bit unstable right now, but not too bad. So yeah, sorry about that, internet issues, but we're still compiling. So the drum roll is still going on, and yeah, the website's working now. And what I wanted to show was that the story for Windows is okay. It's still not working. Yeah. So if you click on Windows here, it says, "Oh no, we currently do not have any Windows machine available to test Accelerate on. If you're trying to install Accelerate on Windows, let us know on the mailing list or issue tracker how it went or how you went. Especially if you are successful, please let us know the procedure you used so that we can update the instructions to help others." So that's it. You see, that's well done. Call for help was definitely answered and gave me some extra fuel to try and carry on, soldier on, keep calm and carry on. And I think we got to a point where it will shortly work. Of course, there's still some stuff like, is it going to succeed in actually creating a window for a GUI-based application? That I don't know. Also, I totally want to compare that with, maybe I will indeed in the end build the NBody example that ships with the SDK, with the whole Visual Studio, not Visual Studio Code, but the whole Visual Studio. Let me check my task manager, see if things are still compiling. Yeah, GHC is hugging one of my cores. Only one, actually. Yeah, I guess now that it compiled all of the individual modules, it still needs to compile the NBody code, though, from the example itself. And this is still a library. So maybe would that call out to LLVM? No. At the linking phase, it might be linking with LLVM, and I imagine that there's a lot of crunching to do for that. Yeah. So let's check out which issue tracker we're talking about. This one, okay. So I think we could maybe even venture into trying to do that. Yeah, CPU we know is related to another issue. And what are some of the Windows things here? Unexpected launch failure on Windows? No. Oh, that's old. But it worked. With nightly version, so supposedly this has, so maybe this dates from a time where actually there was a Windows machine with one of the developers. Oh, mirror stencil boundary condition. Sec falls reliably on the machine. I'll try with two versions of LLVM, and with PTX there's an illegal memory access. Huh, interesting. And and then one of the developers says it might fix it. Let's see about Trevor McDonald. Still building. Using 1.6 gigs of memory. Not too bad. Assistant professor in the software technology group at University of Utrecht. Seems like a hotspot for Haskell developers. And last paper, accelerating nested data parallelism with a video. Yay, I have something to look at again. Yeah, working with Gabriel Keller. I saw Gabriel Keller's talk at BobConf a few years ago. And fortunately, this doesn't work. Well, I suppose we can go see the source code. And that will be here. Papers. And that would be this one, right? Yeah, we got it. But why didn't it work there? No reason. Just some more Windows weirdness. Oh boy. Okay, irregular nested data parallelism. We're still building here. GHC still churning. Okay, I didn't want to do that, but apparently I don't know how to undo it. Sorry, I'm doing something off screen. I end up with this version of the task manager, and I don't know how to. I double-clicked on it, and of course, double-clicking on it again doesn't undo the first double-click. I mean, why would you use such a simple UX design pattern, right? Okay, well, escape actually worked, so I can't, I guess, retrieve it. Okay, yeah, I got it. I got it again this time. Hello. And where is yeah, GHC is there. Okay. All right. Irregular nested data parallelism is a powerful programming model which enables the expression of a large class of parallel algorithms. Notoriously difficult to compile such programs to efficient code for modern parallel architecture. Regular data parallelism, on the other hand, is much easier to compile to efficient code, but too restricted to express some problems, or in a manner to exploit the full parallelism. We extend the regular data parallel programming model to allow for the parallel execution of array-level conditionals and iterations over irregular nested structures, and present two novel static analyses to optimize the code generated for these programs, which reduces the costs of this more powerful irregular model. So I guess that conditionals, array-level conditionals and iteration is a kind of a smaller language, and then through that they can actually make it run super fast. We present benchmarks to support our claim that these extensions are effective as well as feasible, as they enable to exploit the full parallelism of an important class of algorithms, and together with our optimization lead to an improvement in absolute performance over an implementation limited to exploiting only regular parallelism. So that's the key aspect here, is what is the class of algorithm that actually can be expressed with these extensions of array level conditionals and iterations. So let's go to the graph, because I'm visual. We're still compiling. And well, so it seems like we mostly have quicksort and Fourier transform. And this should work in LLVM 9 and Cuda 10.1. Sorry about that. Yeah, quicksort first Fourier transform. So yeah, unfortunately, no such thing as graph computations yet. Okay, let's download this. And yeah, so I think that's one of, I mean, that's one of the one that I'm interested in, but I guess that's still good progress. Also doing this not in as a GHC plugin, which was what Simon Pettenjohn was doing, but as a library also is probably a good testament to the fact that doing high performance stuff in Haskell is becoming more reliable these days. So there's some shape analysis and okay, well, I'll definitely check out the video. That's really cool. I'll actually leave this and I'll put it on the links. Ghostbuster, a tool for simplifying and converting GDTs. That sounds pretty cool. Never heard of that. Oh, Ryan Newton, that sounds familiar. Functional high performance numerical computing, yeah. We want those things. Accelerator LLVM, very nice. Accelerate is definitely what we're looking at. Very cool, very cool. So very much an active contributor to Accelerate. In fact, to push the boundaries of Accelerate to nested data parallelism, which is definitely a research frontier, and it's been for quite a few years. So that's super exciting. Okay, GHC, you're still doing things. You are still on only one core. I don't know if I can do multi-core from Windows here. But you know what? My 2 hours of streaming are done, and that means that there's a bit of a cliffhanger here. But I think we made significant progress in this subtask of trying to get this accelerate backend GPU backend to compile on Windows, which is a path that hasn't been open. So we are rendering some service to the community of people who are interested in high performance computing and Haskell and are stuck on Windows. I'm not stuck on Windows, but I don't know why I did this. But hey, after all, why not? And then once we're done, we can play a little bit with it, and that's going to be interesting. And the fact that there is now nested data parallelism, and let's take a quick look. Sorry, I can't close it quite yet. I want to find out whether that's actually implemented in at least a branch or something. Is there some reference to the code? There is. Example quicksort. So hold on, that's user. A loop-based implementation of the quicksort algorithm, which is representative of irregular divide and conquer algorithm, is basically chosen because it has minimal computation and data movement. Iteration leaves the shapes of the subarray and change so we can be optimized as regular nested data parallelism. Our optimized version is 6 to 13 times faster than the unoptimized accelerate program. And Futark, which we've talked about in previous streams, which is this dependently typed language focused on array computation, and that does nested data parallelism is mentioned here. And for small arrays, the GPU is not fully utilized, but for larger arrays, the approach has lower overhead and overtakes our implementation. Got it. They also compare with FFI, which is great. Incremental flattening. Also, it means that larger arrays actually are not quite yet doable or most performant. The incremental flattening approach of FFI is orthogonal to this work, so it will be possible to utilize both approaches simultaneously. Amazing. Ooh, that's an interesting area. And right. Our work is open source. Beautiful. Thank you so much. Really appreciate this. And it's a different contributor, also from Utrecht University, and it's just a fork of Accelerate. Yeah. So, and it's only, oh, so it's actually, there is a feature branch in Accelerate for sequences, and it's just not exactly, well, it hasn't been kept completely up to date with the latest version of Accelerate, but there is awareness of it, and but there's no open pull request for it. So I suppose it might be a lot of changes to review. Also, Accelerate is not a company, so it will take a little bit of time if it's happening in the academic setting. And Manuel Chakravarti has been helping out. All right, so we might be even able to test this fork at some point and see for ourselves some of these things. Right, so how does it overtake it? We're talking about the they call the new implementation Accelerate Regular. I see. Okay, so we are talking about an order of magnitude. Once we get past only the thousands, actually. So quick sort for 1,000 array, 1,000 size array. I don't have it'll be interesting to have C, of course, for this. Fourier transform, is quite exciting as well. Because this is used for, digital signal processing. I'd be interested, I want to also at some point in the stream to start looking at things like machine learning and see how we can, have Haskell maybe as some glue on top. And to be honest, that's another, if we do look at machine learning, then it would be a good excuse to also start playing with Julia, because the Julia ecosystem around machine learning is actually really active. And then in Julia, there's some really interesting things happening in the category theory world that are actually really, I think, have the potential for doing the type of integration of scientific research that hasn't really happened before. So that's it. Thank you so much for watching. I will be back on this topic next Thursday. So that's in 2 days, same time. And then tomorrow we're back on the prototype, our browser prototype that uses the Chronophore library that we built. So please come back and tune in and, do all the following and liking things. And I'll see you later. Bye-bye.